as we start reviewing our vector addition, let's think about what has to happen when we add vectors. Okay, first of all, if we have a vector at an angle, what's the first thing that we have to do? If we see something at an angle, what do we have to do? Find the sides, right? Break it into its x components and its y components. We don't deal with things in physics that are both x and y, right? We deal with them completely separately. So as we go through these problems, this should be a review for you, a total review, okay? And this first problem, it says a person walks 1 kilometer north, 5 kilometers west, 3 south, 7 east. We want to find the total displacement. So how far he is exactly from where he started, okay? So this problem has how many vectors we're going to add together here? 4. All right, so let's go ahead and start looking at this. Our first vector is 1 kilometer north. So if I say v1y, that's going to be positive 1. What would v1x be? 0. Yeah, because it only has a y component. Moving on, v2y would be 0. Good, because it's going west. And that means v2x would be 5 or negative 5. Negative. Why do we include the negative there? West. Yeah, west, right, the negative direction. So the third vector is 3 kilometers south, which means v3y would be negative 3. v3x is equal to 0. And our last vector, v4y equals 0, and v4x equals positive 7, because it's going east. Okay, so this problem was pretty easy. We didn't have to break in any angles into components. These gave us all 4 vectors that were purely horizontal or purely vertical, so pretty easy. Okay, we're going to add all our x's and add all of our y's. Okay, so for the y's, negative 3 plus 1 is negative 2. For the x's, we have negative 5 plus 7, which is positive 2. Okay, so in the y direction, can we expect that vector component to go in north or south? South. South. And for our horizontal component, are we going to have it go east or west? East, because it's positive 2. Okay, so we've got the components to our resultant vector. What's the last step here? Yeah, we build our new triangle, find the hypotenuse, right? Is that coming back to us a little bit? Hopefully. Okay. A little bit, maybe. Okay, so we need to go south 2 and east 2. Doesn't matter which direction you go first. Our resultant would look something like this. Right? He's going to end up at this point from where he started. So we want to find the hypotenuse of that as well as the angle from the origin. Okay. How do we go about solving for the hypotenuse of our triangle? Yep, good. Pythagorean theorem. I'm sorry, tell me one more time. 2.82. 2.82, okay. And what would our units be there?
Meters.
Kilometers, yep. Okay, is that the only thing we need for the displacement? No, we need this angle right there. Okay, and so if I want to find that angle, I have the opposite side and the adjacent side. So what trig function should I use? Second tangent. Right, second tangent in the second button because I'm solving for the angle. Do we have to do it if we can obviously see that they're both the same?
Yes. No.
You can plug it in your calculator. What angle do you know it's going to be?
45.
Hopefully we see that. Okay, at 45 degrees. And 45 degrees, if we look at this particular diagram, is that east of south or south of east? East of south. Okay, this particular diagram is east of south. You draw it the other way, it'd be exactly the same thing, but south of east. Okay, is that coming back to us a little bit? Hopefully. Okay, good. So it says an aircraft climbs at 200 meters per second, 20 degrees to the horizontal. Determine the horizontal and vertical components of its velocity. Okay, what is the words or this phrase with respect to the horizontal, what's that mean? Where do we draw our angle? What do you think? Do we remember?
I don't want to say equal, but
I kind of think you may be going in the right direction. Okay, here's our origin. Here's our starting point. So when we draw an angle with respect to the horizontal, that means we look at the positive x-axis, right? The positive horizontal axis, which would be here. And we draw our angle up from there. So it's always north of east. Okay, so with respect to the horizontal means it's always north of east. So this angle would be 20 degrees. This would be 200. Okay, so the components of this would look something like that. Okay, let's go ahead and solve for those components. This portion right here, you have to be able to do. Okay, to be successful in Chapter 6, you have to be able to break that, those sides down. Okay, so we see the hypotenuse, we see the angle. We need to solve for the velocity in the y direction and the velocity in the x direction. Okay. So to solve for Vy, we're going to take the hypotenuse times sine or cosine. Sine, because Vy is opposite, and the hypotenuse is the hypotenuse. Okay, so we'll take 200 times sine of 20, and that should give us what? 68.4. And what's our units probably?
Meters, yeah. Meters per second.
Meters per second. It has to match the hypotenuse. And the hypotenuse is 200 meters per second. The components should always match the whole, right? Components make up the whole, so it has to match. Vx is 200 times cosine of 20, which should give us a lot bigger number. 187.9 meters per second. Okay? Okay? We're going to start looking at projectile motion. And in projectile motion, we have to analyze vertical and horizontal components separately. So that means you're going to have a horizontal velocity and a vertical velocity. So in these two problems, that's what you did. You took this initial velocity, right, at some angle. So something's moving through the air with some certain speed at an angle, and you broke it into how fast is it moving vertically and how fast is it moving horizontally. Those are two components that are separate of each other. These two problems give us a really good kind of segue into what's going to be happening in Chapter 6. So this will be how you start a lot of problems in Chapter 6, is by breaking down those two things. Once you have the initial horizontal velocity and the initial vertical velocity, you can solve for lots of other things, right? You can solve for the time, or the distance traveled, or how far it fell, things like that. Okay? That's all we're going to do with vector components, so you can put that sheet up. You can finish the rest of those if you have time at some point for more practice if you want to. So we're going to talk today about something called projectile motion. Okay? Projectile motion. Projectile means it's an object that moves through the air in 2 dimensions. 2 dimensions meaning horizontal and vertical. Okay? So can anyone give me an example of some things that move through the air both horizontally and vertically?
Okay.
electricity.
An airplane taking off, yeah, okay.
Like,
No, not electricity.
no, that's dumb. Vomit. Projectile vomit.
Yeah, a pleasant picture, but yes, that would work.
No, I'm like.
I understand how it works. Yes, that is a good example. Yes. Anything else? Right? In sports, we see projectiles all the time. Right? Listen. Anytime you kick a ball or throw a ball or hit a ball or do anything in sports, basically you have projectile paths. Right? Projectiles are anything that moves through the air both vertically and horizontally. So these are some examples. Almost anything you can think of in sports specifically deals with projectile motion. Okay, a golf ball, when you tee it off, it will go reach its peak height and then it will come back down. Right? My golf ball might not get off the ground, but they should, theoretically. Okay, it should go up in the air, move horizontally, and come back to the ground. So all those are examples of projectile motion. Right? When we talk about projectiles, we are not concerned with how the object got started in its motion. We don't care about the kick. We don't care about the throw. We don't care about anything that puts the object into motion. What we're concerned about is what happens basically once it becomes a freely falling object. Okay? So an object that is freely falling means that it's no longer connected to anything. No forces acting on it, no direct forces, no contact forces acting on it anymore. There's nothing that's keeping it in place beside gravity and its path, right? Its projectile path. Does that make sense? So we don't care about the kick, we don't care about the throw, we don't care about the object before it leaves the table when it rolls to the ground. Okay, we don't care. When we look at an object in free fall, or that's freely moving through the air, we have to take into consideration that the acceleration is negative 9.8 meters per second squared. Okay, negative 9.8 meters per second squared. So that is also what? What do we call that? Negative 9.8 meters per second squared. What's it called?
Gravity.
Gravity. Okay? We need to understand and make sure that we plug in that it's negative, which tells us it's going in what direction?
Down.
Okay, so even if an object is moving upward through the air, what direction is gravity?
Down.
Still down. Always negative 9.8. Always. Okay? And this acceleration is only in the vertical direction. We're going to have something different we'll talk about for horizontal acceleration. Okay, when something is flying through the air in a projectile path, it has something called a trajectory. That's the path that it follows. Can anyone tell me kind of what a projectile motion looks like? Like, show me like with your arm. Like, is it wavy or is it up and back down? Good, right? Projectiles go up and then they come back down. There's another type of projectile called a rolling projectile that we're going to talk about today. It's basically when an object leaves a cliff or a table, right? If I roll something off the table, it's going to move both horizontally and vertically until it gets to the ground. It's not going to reach a peak height and then come back down. Yeah.
Are we doing that?
Okay, so these are our original kinematics equations. This is our new equations just for projectiles. Okay? The only thing that really changed is we got a couple new subscripts. Okay, and the reason that happens is because these equations are only for things that are moving vertically. Okay, so these are the vertical components of our projectiles. Okay, so on that equation sheet, I would make sure that you wrote projectile equations, right? And you put in the y direction or vertical or something like that. Okay, you need to make that very, very specific. You also probably don't need to include this little y here on acceleration, since we know acceleration in the y direction is always negative 9.8. That's up to you, but you are welcome to if you'd like. Okay, I just took them exactly from your book. So since it's been a little bit before we looked at our kinematics equations, or a little while since we have, let's talk through what these variables and their subscripts mean. Okay, V stands for velocity. The y tells us it is what? Vertical, and F tells us
Friction.
no, final. So this is velocity in the vertical direction, final. So this is final vertical velocity, okay? So that would make this variable what? Initial vertical velocity. Okay, you can kind of read those backwards. Listen. Okay, in our normal kinematics equations, what variable goes here? Distance, yeah. So instead of a d for distance or displacements, we put a y. Is there a reason for that?
So that's peak height.
Yeah, it's height, right? That's what we're looking at here. We're not looking at horizontal distance, we're looking at vertical distance, which is why we put a y. So this is the final height, and this is the initial height. Okay? This would be final vertical velocity again here, initial vertical velocity, distance final, distance initial. T is still time. Acceleration in the y direction is always negative 9.8 meters per second squared. Okay, any questions about these variables or these equations? Okay. We make a couple assumptions when we deal with projectile motion. I'm going to explain these before we move on to our next set of equations, okay? When we deal with projectiles, we always ignore air resistance. basically just like we had before. Okay, the only time we took into consideration air resistance was in the forces chapter. Okay, we're going to assume the motion always begins at time equals 0. Okay, so we're never going to have a final time and an initial time. Right? The time it takes for an object is going to be just the difference. Okay, we also get to pick where we put the origin, right? Pick where we put the crosshairs of our coordinate system. And we're always going to assume that the origin goes at the beginning of the motion, okay? Or that the motion begins at the origin, either way you want to think about that. Okay, so let's look at an example of maybe one we would do today. I've got a cliff. I'm going to dive off the cliff and land somewhere down here. Okay, that's what's happening. The origin then would get set right here. So this would be my starting point. Time is 0. My initial vertical distance or displacement is 0. My initial horizontal displacement is 0. Okay, so by choosing this origin to be at the beginning of the motion, that tells us that xi is 0 and yi is 0. Okay, that's what that does for us. It tells us that our initial positions are both 0. Okay, that's what we just talked about. If you put the origin at the beginning of the motion, both of those will be equal to 0. We don't use d anymore to represent displacement. We use x and y. Okay, so you need to pay attention to that in your kinematics equations. The last assumption that we make, and that's going to play a role in our horizontal equations, is that the acceleration in the x direction is 0. Right? We talked about how things don't randomly speed up or slow down in the x direction. That means that there's no change in velocity, which means there is no acceleration. Okay? Things don't randomly speed up or slow down. Gravity's not having any effect on the horizontal motion. So acceleration in the x direction is equal to 0. Okay, so that's going to change our kinematics equations quite a bit.
Is that all the time?
All the All right, let's look at how we get from the long version to the short version. Okay, if we look at this first equation right here, we see that final velocity in the x direction, sorry, I know this is cut off a little bit, is equal to initial horizontal velocity plus acceleration times time. What is acceleration equal to? 0, which means I can take this whole term out. Okay, which means it looks something like this. Okay, that's it. This is telling us that the final horizontal velocity is equal to initial, right? There's no change, no acceleration, so that's an easy one. This first equation doesn't tell us a whole lot except for final is equal to initial. Okay, so we don't plug things into this equation. The second one, x final equals x initial plus vxit 1/2 at squared. What's the acceleration in the x direction? 0, which means we can get rid of that whole term. Okay? What is the initial position most of the time? 0, so I can get rid of x sub I. That leaves us with x final vxit. Okay, so all we're doing is abbreviating these horizontal equations. So that leaves us with this equation here. The third one, vxf squared vxi squared 2a. This whole thing, since it has a horizontal acceleration, would be 0. We can get rid of that whole term, which leaves us with vxf squared equals vxi squared. Is there any reason for us to have this equation and this equation? No. They mean exactly the same thing. There's no reason for us to have both of them, so we don't. Okay, so here's our two equations for the horizontal components of projectiles. Okay. Take a look at your two sets of equations. What's the one variable that floats between them? What's the one variable that is in both equations?
Velocity final.
The subscripts mean something. What's the one variable that you can use in both equations? Come on. One variable that is independent of horizontal and vertical. Time. Time. That's it. Okay? I'm sorry, I want you to look at the sets of the vertical equations and the horizontal equations. Okay? Time is the connector between horizontal and vertical equations. Okay? So between the x equations and the y equations, time is the only one that can go between the two. Okay? So that's the one that you have to use to connect those two sets of equations. Okay?
Were you just talking about that first and second one?
Which of these do you think would hit the ground first? Right? An object that rolls off the table or an object that's dropped from the height of the table? Which is going to hit the ground first?
That dropped.
Okay, how many of you think dropped? And how many of you think the ball that rolls off the table will hit the ground first? Okay, and how many of you think drop? How many of you didn't vote?
It'll be dropped because when you roll it, it'll have a trajectory, so it won't be going straight down.
Okay, what do we know about the vertical and horizontal components of a projectile? They don't matter. They don't matter to each other. So, they're going to hit the ground at the same time. At the same time. Okay? So, listen. As a ball rolls, boys, as a ball rolls off this table, it's going to move horizontally as well as drop to the floor. Okay? As I drop a ball from the exact same height, the only thing that matters as far as how long it's going to take them to hit the ground is the height at which they fall from. Okay? The horizontal and the vertical components are completely separate here, independent of one another. So here's kind of a time-by-time picture of this exact situation, right? The yellow ball has been projected. The pink ball has been dropped. Does mass go into the kinematics equations? No, it does not. Okay, no, it doesn't matter what they weigh. The mass does not make a difference. Okay? The only thing that makes a difference is the height at which they're dropped from. Okay? Okay. I cannot continue to talk over you. Okay? I cannot continue to talk over you. You have to be focused. Okay? You can do it. Don't point fingers.
I'm always focused.
All right. When we solve these projectile problems, it's extremely important that you read the entire thing. Don't assume you think they know what it's going to ask, because you are probably going to be wrong, okay? And then you're going to waste a lot of time. These problems might require 2 or 3 equations to get to your final answer. So you have to make sure you understand the process that goes into it and you read the whole entire thing. Okay? Choose an origin and an XY coordinate system. The coordinate system is going to stay the exact same that it always has been, right? It's going to be just like this, positive direction, negative, and negative. You get to put the origin where the start of the motion is, so you need to pay attention. Is the object starting on the ground? Is it starting on a 50-meter tall cliff? Where is it starting from? The origin goes there. Okay? Analyze x and y separately. Make your list of your variables and your margins, right? You might have 6 or 7 variables per problem. If you are not staying organized, it's going to be rough for you, okay? Make sure that you keep those things organized. Okay? Vx, or the horizontal velocity, never changes. What's the velocity of an object at peak height? Yeah? Okay? The velocity of an object at peak height, the vertical velocity, is 0. The horizontal velocity of an object at peak height is whatever it was to start the motion, right? It never stops. So horizontally, that object never stops moving. So at peak height, it's going to go move. It's going to stop moving vertically, but keep moving horizontally, and then we'll fall back down and begin its vertical descension.
Why would we put negatives, seeing as how if it drops down, like it can't go past?
Yes.
Okay, first practice problem.
Why do we study?
Okay, let's go. Get it written down where you need to. Get a calculator out if you don't have one out already. You should already have one out. All right, so let's go ahead and draw what we think's going on here. Okay, here's my cliff. He's going to leave horizontally. And then eventually fall to the ground. Okay, so as he's moving through the air, he's moving both horizontally and vertically. Okay, where is my origin going to go? Top of the cliff, right? Where the motion starts from. Okay, so that means my initial displacement in both the vertical direction and the horizontal direction is 0. Okay, so let's talk about a couple other things here. My height of my cliff is 50 meters. And the distance that it's going to land from the base of the cliff is 90 meters. What two variables do those tell us? X final and Y final. Okay? Final displacements. Wow, you can't see that. Okay, sorry. Okay, so X final is going to be 90 because it's landing positive 90 meters from where it started. What's the Y final going to be?
Negative 50.
Negative 50. Y final is negative 50. Y initial is 0 because this is its starting point. So if I put this on a coordinate, on a grid, and my final is going to be down here, that's going to be negative 50. Okay? So my Y final is negative 50. Okay. What is our question asking us for? How fast, right? I'll move this up here. So how fast must the motorcycle leave the cliff to land 90 meters from the base? So that means we're solving for a final velocity. Okay? As this guy leaves the cliff, he's traveling purely horizontal, and then he will start to drop. So this is what we call a rolling projectile. He's leaving the cliff with only horizontal velocity, and then it will start to pick up vertical speed. Okay? So that means we are solving for velocity in the x direction. Okay? And could we say either I or F? Does it matter? Velocity x, does it matter if we say initial or final? Not really, right? They never change. Velocity in the horizontal direction never changes, so it doesn't really make a difference if we say initial or final. Okay, we're trying to solve for what it's going to leave the cliff at, which would be initial. Either way, okay? Let me tell you the one other thing that we know from this problem. Okay? We know that this object is leaving the cliff with purely horizontal velocity. What does that mean about the initial vertical velocity? 0. There's none, right? If he's leaving with purely horizontally, he speeds horizontally off a cliff. He dives horizontally off a diving board, whatever it is, okay? If it has these kind of buzzword here, speeds horizontally, that tells us that Vyi is equal to 0. That's a big, big, big point. And that's a big characteristic of what we call a rolling projectile. Okay, understood? All right, let's look at an equation that we need to solve for Vxi. What equation do we need to solve for that, Vxi? Take a look at your equation sheet. If we want to solve for Vxi, what else do we need?
Time.
Yeah, we need time, right? Here's the equation right here that we would probably need. Do we have time? No. Okay. But time's the one variable that can travel between vertical and horizontal. So now we jump to our vertical equations. And we try to find a vertical equation that we can use to solve for time. So take a look at your vertical equations. Do we know final vertical velocity?
No.
Nope.
The second
Why the second one?
Because that's the only other one with time.
It's the only other one with time. Okay, yes, that would do it. This equation right here, the second one right here, the one that's listed, that equation you will almost always use to solve for time. Okay, you'll use it a lot to solve for time. Okay, so let's go ahead and start plugging in here. Y final we know is negative 50. Y initial we know is 0. Vyi we know is 0. 1/2, what's A in the vertical direction? Negative 9.8. And then we have t squared. That'll leave you negative 50 equals negative 4.9 t squared. Okay, divide negative 4.9 over. You get a negative time, that means something went wrong. No, no time travels. Probably a calculator error. Okay, so for time, what did we end up with? 3.2? I would agree with that. Okay, does that answer our question? We want to know how fast it left the cliff. Okay, so now we can look back to that equation we knew we needed to use. And we could say 90 meters equals Vxi times 3.2 seconds. Yeah.
Joy got something else. How do you
Did you forget to square root it? Did you get 10 point something? Or 9? Yeah, okay. Square root. That's all right. I'm sorry, our initial velocity came out to be
20.125.
meters per second. All right, rocks thrown horizontally from the top of the cliff, 24 meters high. Horizontal velocity is 3.21. For how long is it in the air? How far from the base does it land? And what's the final vertical velocity? So we are going to ask lots of questions here. Okay? Go ahead and get written down what you need to. Get your diagram drawn. Okay. Good. Vx, right? And we can call it initial or final. It doesn't matter. And what is that equal to? 3.21. Perfect. Okay. What else does this tell us specifically?
The Y.
What y?
Final.
Y final. Okay. Tell me what y final is.
Negative 24.
-24. Okay. Good. I meant this piece right here. Okay. What does that tell us? What's that tell us about the vertical velocity, the initial vertical velocity? No. What's this buzzword tell us here? It's thrown horizontally. That means that the initial vertical velocity is just 0, right? When it leaves the cliff purely horizontally, that means at that point it has no vertical component, right? It only has a horizontal component. So vertical velocity, if it's purely horizontal, that means that there's no vertical component to it. Okay? Anything else we know here? We know gravity. We know our initial positions are both 0. Okay, so what equation should we use to solve for time? Yeah, the second vertical. Okay, we're going to use that one a lot.
I have a quick question.
So how long is the rock in the air? We use the second kinematics equation, the vertical direction. We solve for time. Okay. How far from the base? What variable does that mean we're solving for? X final. Okay, so how far from the base does it land? That means we're looking for x final. Whoa. Okay, and that's going to be Vxi times time. Do we have both of those things? Vxi and t? We sure do. Take 3.21 times 2.2. Gosh, dang. 7.1 meters. Sorry, I know it keeps getting cut off on this side. I need to move my projector. Okay, and then final vertical velocity. We got to use our vertical set of equations. Which one should we use? Yeah, we can use the top one, the easy one, right? I'll change colors here so I see it different. Okay, so that means we would say VYF equals VYI plus AT. This is what we're solving for. VYI is 0. And should our final velocity come out here positive or negative? Yeah, negative. Okay, does that make sense? Does it make sense that our velocity is negative? Is our object going up or down? It's going down, so it should make sense that it's negative. Okay. What questions do we have? Okay, these are rolling projectiles. Next class we'll get to something called launched projectiles, which means it's going to leave at an angle, go up and reach its peak height, and then come back down. Okay, so these are rolling projectiles. This is a different kind. All right, you're going to do this last one on your own.